Let's start with part A. I want to approximate the rate of change of the number of vehicles in line at t equals 10 minutes. Because I want to approximate the rate of change, I'm going to end up using the slope. And the number of vehicles is L of t. Okay. So that's L of t at t equals 10 minutes. So for this one, I can find the slope by using a couple of points. So I can use the points around 10. So I can use 0, 10 and 10, 60. Or I can use the points 10, 60, 30, 100. Or I can use 10, 60 and 0, 10 and 30, 100. So any of these will work. Okay. So this slope is going to be delta L over delta T, which the number of vehicles is V, we'll say, and then T is M, so time is in minutes. So we're going to subtract the number of vehicles over time, and we're going to get 5 vehicles per minute. And then same thing here. We get 2 vehicles per minute. And then last one, we're going to get 3 vehicles per minute. So any of these 3 answers is acceptable for part A. Okay. Let's move on to part B. We want to find the rate of change of wait time when 60 vehicles are lined up, and then indicate the units of measure. Wait time is defined by W of x. That's a waiting time in seconds. 60 vehicles, well, x here is the number of vehicles, so we're looking at 60 vehicles. That gives us x is 60. The rate of change is the derivative. So combining these two, we want to find the derivative of w at x equals 60. For the units of measure, you can think of the derivative as delta w over delta x. W is the waiting time in seconds. X is a number of vehicles, so we'll just say V. So that's going to be the units. Now let's actually find the derivative. So W of x is 20 sine of pi x over 180. If I take the derivative, I'm going to use the chain rule. So I'm going to take the derivative of the outside, keep the inside the same, and multiply by the derivative of the inside. So the 20 and the 180, that's going to change to 1 and 9. So that's going to be pi over 9 times cosine pi x over 180. Finally, I'm going to plug in x equals 60. So I'm going to get pi over 9 times cosine 60 pi over 180. So this thing is just going to be pi over 3. So cosine of pi over 3 is a half. That's times pi over 9. And so that's going to be pi over 18 seconds over vehicle. So seconds per vehicle. Okay, so the waiting time at, let's see, for 60 vehicles is pi over 18 seconds per vehicle. And here's, when I said 60 vehicles, that's when 60 vehicles are lined up, the waiting time is pi over 18 seconds per vehicle. Okay, so next we're going to be looking at part C. We want to approximate the integral of 0 to 60 of L of t dt using trapezoidal sum, and we want to indicate the units of measure. So here, because we're using L, so L is the number of vehicles, so we'll say V. L prime, you can think of it as like a slope. It's like delta L over delta T which is vehicles per minute. So whenever you take the derivative, you're going to be dividing by time. So like if I was to take the second derivative, this will be vehicles per minute squared. And then the third derivative will be vehicles over minutes cubed, etc. So if I take the antiderivative, I'm actually going to be multiplying by the time. So if I want to go back to the antiderivative of L, that's going to be the vehicle times minute. So that's going to be the units here. And I want to find I'm going to use the trapezoidal sum. So if you want, you can graph this to visualize it. But basically, L of t is going to be the base of my trapezoid. We'll say bases. And then t is going to be my height. So this seems kind of opposite. But for the area of a trapezoid, I'm basically taking the average of the two bases and multiplying it by the height. So this is how it goes. So we always start with 1/2. Base 1 plus base 2. So we're going to use the first two. The height will be the difference in the t values. Okay, then we move on to the next two. We go to 60 and 100. Those are going to be my two bases. My height changes from 10 to 30. So that's 20. The next two is going to be 180. The height changes from 30 to 45. So that's a change of 15. Finally, I want to go up to 60. So this is going to be the last one. My two bases are 80 and 90. And my height changes from 45 to 60. So that's going to be 15. So if I multiply and add these all together, I get 4,575 vehicle minutes. All right, so that's part C. Now let's move on to part D. So we want to see the fewest number of times at which L prime of t must equal 0. Okay. So first, if we look at this, L is defined to be twice differentiable. So that means you could take the derivative twice and it'll be continuous. So because L is differentiable, that implies the mean value theorem applies. Okay, now let's look at what's going on here. So let's say this is my L prime, and I'm just going to plug in different values. So I'm just going to plot all these different t values. So I don't want you to confuse this as the first derivative test. This is just strictly what's going on. Okay. So between 0 and 10, the derivative increases. The derivative is positive because L increases. It goes from 10 to 60. From 10 to 30, it increases from 60 to 100, and then it decreases from 100 to 80, increases from 80 to 90, decreases from 90 to 50, and then decreases again. So this is what's happening. Okay. So because L is continuous, L prime is continuous, and we know that because it's twice differentiable, the intermediate value theorem applies. So when it changes from, let's say, increasing to decreasing, like this one right here, it changes from positive to negative. So that means that because it's continuous, it has to hit 0. And over here at 60, it has to hit 0 because it changes from positive to negative. And also, let's not forget 45. That changes from negative to positive. So that means it has to cross 0. So there's 3 cases here. At least 3 cases where the derivative is 0. So the answer would be 3 times. So it's at least 0 for 3 times, for 3 values. Okay, so you want to make sure you mention these 2. These are critical to answering this problem. Now part E. So suppose that at t equals 10 minutes, the vehicles join the line at the rate of 8 vehicles per minute. We want to find the rate of change of the waiting time at t equals 10. Okay, so we want to use make sure we use the correct units and explain the meaning. Okay, so find the rate of change of the waiting time. So the waiting time takes an input x, where x is a number of vehicles lined up. You see how t equals 10 is not the input for w? One is time, the other one is number of vehicles lined up. So we cannot say, w prime of 10. This is wrong. But what we can do is introduce or compose L of 10. Because L of 10 is going to give us a number of vehicles at t equals 10, which is the same thing as x. So we're going to call L of 10 our x. The units match up. So we want to find the derivative of this thing, which is the same thing as, using the chain rule. So it's the same thing as this. Now, the vehicles join the line at the rate of 8 vehicles per minute. So that's going to be my L prime of 10. So that's going to be 8. L of 10, well, I go over here. L of 10 is 60. So I'm going to look at W prime of 60 times L prime of 10, which is 8. W prime of 60 was actually what we found out in part B. We found the rate of change of wait time when 60 vehicles are lined up. So that was pi over 18. And we multiply that by 8. Let's see, we get 4 pi over 9. Now, what are the units? Okay, so this one we have to be very careful. We're multiplying by 2 things. W prime is basically change in W over change in time. I mean, it's technically, okay, so it's really W, it's dW over dt, right? Which wait time, W was in seconds. The waiting time is in seconds over t, which is, actually I should say x, right? X is the input, and x is the number of vehicles that are lined up. Okay. So it's seconds over vehicles. Okay, L prime is dL over dt. L is the number of vehicles. T is the time in minutes. So I'm going to be multiplying these 2 things. Okay. So W prime, that's a seconds per vehicle. L prime, we said, is vehicle per minute. Cross these off, we're given seconds per minute. Okay. So those are going to be the units for the derivative of WL of 10. And what does this mean? Well, this means that at t equals 10 minutes, the waiting time is increasing by 4 pi over 9 seconds every minute.